Welcome back. So we want to prove this theorem that a non-zero non-unit integer n is a prime number if and only if it is an irreducible integer, and you have to recall from the previous definition what we mean by an irreducible integer and what we mean by a prime number. So let's assume that, so I'm going to prove, this is an if and only if statement, so I'm going to prove, I'm going to prove only one direction of it. So let's let p be a non-zero non-unit integer, and we're going to assume that p is irreducible, and now we will try to show that p must be, so p must be a P must be a prime number. So to show that P is a prime number, suppose that A and B are integers and P divides AB. And now we need to show that P divides either A or B. Now if P divides A, then we are done, because we need to show that P divides A or B. So if P doesn't divide A, then the GCD of P and A would be 1. So now we can apply the extended Euclidean algorithm, and then we can write the GCD 1 here as a linear combination of A and P. So 1 can be written as a multiple of A plus a multiple of P, and so where x and y are some integers. So then we see that multiply both sides of this equation by b, then we have b is equal to abx plus pyb. Notice that the assumption was that P divides AB, so P divides ABX, and clearly P divides the second term here because it's a multiple of P. So then P divides the entire right hand side here, and therefore P divides B. So we just showed that P. So what we have done is, then if P divides A, then we're done. If P doesn't divide A, then we just showed that P must divide B. Again, the assumption that P divides AB led us to the conclusion that P divides A or P divides B. So as a result, P satisfies the condition for a prime number, so it's a prime number. So we conclude that P is a prime number. So I'm gonna left it as an exercise for you to prove the other direction, that is, assuming that P is a prime number, show that P is an irreducible integer. So I'm not going to left that as an exercise, but the proof is actually in my slides. I'm just not going to go over the proof. Hello everyone. Okay, so that's the proof of the theorem. So there is an extension of this there is an immediate corollary here, that if P is a prime number and if P divides the product or A1, A2, an, then P divides one of the factors AI. And then again, I'm going to leave the proof as an exercise here. So this is just an extension of the definition of the prime number. So recall that if P is a prime number, then if P divides AB, then P divides A or B. So we're just extending that to more than 2 factors here. Okay. All right, so I think I'm going to stop the video here, and then we're going to move on with the next slide in the next video.